Good afternoon, everybody, or good morning, depending on where you're from. Today we're going to talk about modern Fortran, concurrency, and parallelism. We don't call it Fortran 90 or Fortran 2095 or 2003, but simply just call it Fortran. Just make sure that when we talk about Fortran, we refer to modern Fortran. In this 45 to 50-minute seminar, we're going to go over three areas, highlights of some Fortran 2008 standard enhancement, and some concurrency in the loops and a reassignment, and finally, parallel computing with Fortran. Now, before we get started, I would recommend that you get some material so that I can read at your spare time. For instance, I listed a few here. Fortran 2008 features, the book by Metcalf, Reed, and Cohen, Modern Fortran Explained. This is a very good and readable book. And also, if you want, and brief enough, you can download the latest Fortran standard draft. You won't be able to get the formal standard for free, but you can get the draft for free and download it from the internet. Read some of the materials, then you will find more details what the modern Fortran is about and what it can do and what you can make a benefit out of the modern Fortran. Let's take a quick look at some of the Fortran, the latest Fortran standard enhancement in the latest Fortran standard. First of all, it allows you to define array, a constant array, name the constant array without the dimensions. Look at it here. We define an array vals with the 6 elements, but the size or the dimension of this array is omitted with a star. Okay, this is equivalent to declaring a static constant array in C. Okay, you don't have to specify the length or the size of the array, which is convenient. And the second, this is a new way of initializing an array. You define an array, a 6-element array A, then you can assign the values to A in this fashion, which is similar or almost identical to MATLAB. And also, you can assign the entire array to a block of array, another array B in this fashion. So I'm assigning the 6-element array A to the first 6 elements of B. And the third statement here, given a vector A, we can reshape it into a 2x3 array C by calling the intrinsic function reshape, which is quite handy. And these two statements here, and it tells you that you can traverse the elements in this way. At first, we get elements with the even indices, and the next, we traverse the elements in the reverse order from 5 to 1 and the decrement by 1. And also the new standard allows you to put a number of short statements together separated by semicolon, which is kind of handy, so you don't have to put them in 4 different lines. And as well, this do concurrent construct allows you to put a loop with a condition altogether. Here, we loop over I and a j from 1 to n, with the condition I is not equal to j put all together. And this do concurrent construct also allows you to allow the compiler to generate code that can be vectorized and can be executed in parallel or concurrently. Next, the new standard has introduced some new interfaces to mathematical functions. For instance, the first two lines here, these are the traditional functions, but now they can take a complex number x as an argument, which is very handy. You don't have to use different interfaces for different variables with the different data types. So all you need to do is to use the unified interface for all data types. And also, we have the new special mathematical functions. This is the Bessel functions and the gamma functions, earth or air functions. These are very useful and commonly used, especially in engineering applications. And some Euclidean norms. These are two new functions provided conveniently. And also for those who wanted to execute it in the source code, in the Fortran code, to execute external programs, this standard has provided a way of allowing you to run an external function by calling this intrinsic procedure execute command line with the command line. This is the name of a command, and with a number of optional arguments, whether you want to run the command in an asynchronous way, basically you call the function regardless whether it runs or not, you exit, or you want to run it in a synchronous way, you want to, which is basically blocking until it finishes, and then your code can continue. So it gives you some flexibilities. And the next, now these are the declarations of arrays and single variables. So X, A, and B are one-dimensional and two-dimensional arrays. Now, by adding square brackets after the array variables and single variables, you essentially declare shared memory objects. Those objects, the variables, can be shared on a shared memory or even distributed memory systems. And this makes parallel programming extremely convenient. And these features, these objects are called coarrays. Just a regular variable followed by square bracket, and then this variable is declared as a coarray or shared objects. Now the objects can be shared on this shared memory and the distributed memory systems. In the first line here, it says the array X is accessible on the array of 6 processors. And this line, third line here, it tells that this two-dimensional array B can be shared among 16 by 16 processor grid. And these simple variables M, N, UVW, they are also shareable, accessible among participating processes. And the coarray here, there's a concept. The coarray follows the SIMD programming model, single instruction multiple data model. And this is how you will write a parallel program with the coarrays. We will see more example details later on. Now let's move on to vectorization and concurrency, the second part of this talk. Now first, what we see here is a reassignment. The first assignment has a very simple syntax similar to MATLAB, but this can be a little slower for large N. So what's happening here is we define the array already, or declare array somewhere before previously, and then we assign the value, which is a sequence of integers from 0 to n, to the array elements with a single line. And also, we can use this for loop. This is a traditional way of assigning values to array elements. And the loop is traditional and can be vectorized by the compiler. Both way, you can use both the syntax. Now we see here the do concurrent construct. Okay, this is a new language feature introduced to the modern Fortran, or the Fortran currently the Fortran 2008 standard. This is a simple, clean, and tells compiler exactly and not explicitly. There's no dependency between iterations. So the compiler can possibly generate the code that can be vectorized and can be executed concurrently and in parallel. But this is equivalent to this following form, this loop. We put a condition here, A is greater than B. This condition is, and we call the mask. And this is equivalent to put an if branch here in the do concurrent loop, and the compiler will generate the code for you. Now here, what we see is array assignment. We declare two arrays, A and B, and we assign the values of A to B using a loop, or we can use it as shorthand. We assign a block of elements to A to B, or even simply we can just write B equals A. The compiler can optimize the code in both cases without loops at all. Now, let's look at this example. Now, pay close attention to this example. So what we're trying to do here, we have two forms of two codes, which do exactly the same thing, try to accomplish the same task. So what we're trying to do is this. So we have an array, one-dimensional array with elements 0, 1, 2 to 7, and we want to shift. We want to shift the value a bit to this way, or we want to shift a value, all the values forward a bit. Okay. Now, if you look at this problem carefully and do a math, or just do the sketch on a piece of paper a bit, you will see in case 1, when m is greater than 0, so we shift by an index, by a positive index, and then you will find there is no dependency. So we're taking the future value and put it in here, and the next value put it in here, next value put it in here. As opposed to here, when m is less than 0, then we have some backward dependencies. So for instance here, we want to replace 1 with 0, and then 2 with 1. And because we changed the value of the 1 in location 1 with 0 already, and when we attempt to replace the value 2 with the value in location 1, essentially we're taking the new value and putting it here, and this is the result. And this is perhaps not what we want. Okay. Now there is a difference between these two forms, although they are equivalent. In the first array assignment, this array assignment is vectorized and always gives the correct answer no matter what, whether it's greater than 0 or less than this 0. And the second point is the array assignment here might be at the cost of an overhead. And you don't see here, but under the hood, the compiler generate code that uses temporary store on the right hand side. Sorry, there's a mistake. On the right hand side, okay, the compiler uses a temporary store on the right hand side before it replaces the value on the left hand side. Okay, so this way it guarantees that the assignment is done concurrently and correctly, as opposed to a loop here. Depending on the value of the shift index n, you may get a correct answer, or you may get a wrong answer. Okay, the loop is faster, but than the array assignment here, because the array assignment here, the compiler generates the code that uses temporary store, which is very expensive, but it ensures the correctness. So here we're looking at advantages versus disadvantages. Okay, this is something you should keep in mind: the strengths and the weakness of array assignment. Next. So now in this talk, we also focus on one compiler, the GNU compiler, or GCC, because this is publicly accessible and for free. And other compilers like Intel, you might not necessarily be able to get it for free. So if you want to see what's happening in the code generated by the compiler, you can use an option fopt dash, okay, here's a dash dash, f double dash, f opt info optimized, and equals, you give a file name, and then the message will be written to this file, and then you will see some details. It will tell you whether the array assignment, the block is being vectorized or not, or how the loop is vectorized, and so on and so forth. So you have an idea how the vectorization is done by the compiler. Okay, so it just tells you that you can use some options to find more details. Okay, next. Again, this do loop, using loop here, or equivalent, just using this assignment, array assignment. And in this case, this array assignment is slightly faster. And using loops, and the new Fortran standard has introduced a new intrinsic function for the merge. So instead of using a loop, one can also use this form to calculate the mask first, and then just write the 2 lines, which does exactly the same thing as the iterations within the loop, depending on the mask, depending on the value of the mask. So if the mask is true, then we do the first operations. Otherwise, we will perform the second operations. Okay, this is what this function merge does. Depending on the mask, if this is true, then it does the first operation. Otherwise, it does the second operation. And I put up some timings here. The first is using a do concurrent construct, a do loop, and the second I'm using a merge, and the third I'm using another construct, like a where. Okay, these are the timing results, and it turns out in this case, do loop is the fastest, and the second by the use of the intrinsic function merge, and this is the slowest. Now, the other thing I want to point out here is here we see some elements of object-oriented programming. And by using this array assignment and array assignments here, we're hiding the information. We're hiding the operations. But at the cost of some overhead, some temporary stores is being allocated during the operation, which could be fairly expensive. But this is true for all object-oriented programming. And you get a benefit of information hiding, but it might be at the cost of performance. Okay, so let's move on to parallel computing with coarrays. So nowadays we have the computers with the multiple cores or clusters with multiple compute nodes and many cores. So how do you make use of those parallel systems? Without putting any efforts, your program will not run in parallel automatically. You have to write the code in such a way that it can take advantage of the underlying architecture, multi-core or distributed memory systems. So here's an idea for parallel programming. Suppose that, in parallel programming, the concept is we will have multiple processes involved or multiple programs running involved, so that those programs or processes, they work together synchronously or asynchronously on same or different set of data and to accomplish certain tasks. So for instance, I have multiple processes running on the system, working on different tasks and a different chunk of data. And here, typically, I have we're looking at the two processes, one and the process K. Now, process K is holding a chunk of data in the light blue here that the process 1 doesn't have. And the process 1, after the process K, for instance, computed this chunk of data, and the process 1 wants to get this chunk of data from K. Okay, this is the concept. This is the task in the abstract concept. Okay, so we want to get this chunk of data K from K and to put it in here. This is the task. Then you can think of this as an array. We have an array A, and we want to fill up this array, this chunk of array, with the value currently held on process K. Okay, this is the concept. Now, how do we do that? For those of you who are familiar with message passing or MPI, or who have heard of the MPI, this is what's happening typically. So on process 1, we call the rank 1. The rank 1 will place a call to receive data from process K. And we need to know what type of the data we need to receive. It's a real. And from where? From a bunch of processes. The K belongs to a bunch of processes in the community MPI world. So on process 1 or rank 1, we need to have this call. We need to place this call to receive the data, receive the n elements. This is a number of elements from K, and to put them in to the right location. Or more generically, we need to receive the n elements of the data of the real from process K and put them in the buffer, which is temporary storage, and then put the buffer data back into array A. This is the process. And on process K or rank K, we need to send the data. We need to send this amount in number of elements to process A, to rank A. Okay, or in a more generic form, we need to put the data. We need to copy the data from the local A to the buffer, and have the call MPI send to send the buffer the data to process 1. Okay, and of course, and when you write a program, you must make sure that the assembly is done correctly. Okay, so you have to take care of a number of things. But really, mathematically, all we want to do is as simple as this. I just want to have the data from held on process K and to copy over. This is exactly what we want. I don't want to know passing. I don't want to know how to use those function calls. So here comes this notion in the modern Fortran. So all you need to do as a programmer, as an application programmer, all you need to do is to use this notation K. Put the square bracket K here. This tells the compiler I'm fetching the content with array elements from process K and copy them over and put them in my local array. Just as simple as this. One line of code. And this is how it may look like in the actual Fortran source code. So we declare some arrays A, X, U, and A. Now instead of just writing a two-dimensional array A, we just add a square bracket to indicate that this is an array shared among processes. Okay, and this is called a co-array. And so here we're fetching the elements of the array held by process K and copy them over to this array. Now, without square bracket means local array. With the square bracket means this I'm referring to an array or object or variable on a remote process K. Okay, and this is a push. So I'm pushing local array, the content from this local array, and to a remote array A. Okay. Now compared to this previous slide, we're fetching this array from process K and putting the local. And here what we do is in the opposite way. We are pushing the value, local value, to the remote object, remote array K, A. And because we declared array A with a square bracket, means that array A, this array A will appear on all processes. This array A is shared among all the processes. Now, without square brackets, that means that the assignment here is done locally. So I'm just simply taking a block of an array in A here and putting the different location. This is a local assignment. Okay. Now let's take a look at some at high-level concepts and to understand why we need to do this and what's happening under the hood. So conceptually, one process on any computer, this is true, and this is one process. When you run a program, your program runs it on a computer. There's an entity called process. Okay, and this process There's a process 1 and process 2. Process 1 is running on, say, for instance, CPU 1, and process 2 is running on CPU or the core 2. They normally cannot talk to each other. And process 1 cannot access the content on process 2. This is normal. If they can, that will be really dangerous, right? If you can access your neighbor's money inside their house, that will be a really, really bad thing. So the same thing here. In a single entity, the process cannot access data normally held in another process. And in a multi-threaded program or programs, a process will see all the data within this process. This process will run in multiple threads, and on each thread possibly will run on a dedicated core. And because all the threads are still within a single process, so the threads can see the data, can see each other, because they're still within a process. Okay, but a process cannot see the content of another process. And here's the what's happening on a distributed and a shared memory system. We have many processes running on different cores. Of course, this process cannot access the data on process 2, and cannot access data on the process P either, and so on and so forth. In order for these the data exchange to happen, in order for that to become possible, then we have to use a data communication between processes. Okay, there's no other way. So we have 2 running processes, 1 and 2, or maybe 4 here. Now we want to put the orange part, or we want to copy the orange part from process 2 to process 1 in the corresponding location. And this is the high-level expression in the Fortran code. I want to take this chunk on process 2 and put it in here. But what's really happening underneath, under the hood, is there has to be some data communication or message passing taking place in order for this to happen. This is just a high-level syntax. But under the hood, we have to understand something more complicated happening, okay, through interprocess communication, typically MPI, or shared memory mechanism. Okay? So this is just a quick overview of interprocess communications. A quick history about the Coarray. It was first introduced in the late 90s. It was only available on Cray hardware for decades until it became standard, ISO standard. And currently, the compilers that support this Coarray programming paradigm or parallel programming features include Intel, GCC, and G95. G95 is a separate project from GCC. And the support is through, there are mainly there's 2 main streams. One is the Open Coarray project, and the other is done by the people, research team, and the Rice universities. Okay. And as model and the tools for next generation of HPC architecture, and the Coarray, Unified Parallel C, and global arrays, these all belong to what is called a partition, the global access spaces, or PIGAs. And as well, in OpenMP, compiler directive approach, and the OpenNCC are another tool that people can use for parallel okay, parallel programming. Okay, and the coarray belongs to the former partition the global address space. Okay, this is the trend. Now, how does it work? Let's take a look. Take a look at some details. Now, in this example, we declare on the right-hand side, we declared some variables, array variables, and single variables. First, array variables, a two-dimensional variable A, and followed by square brackets. This is the one way of declaring. This is a coarray object with a star, which means tells the compiler we don't have to define how the size of the coarray. The coarray is different. Name coarray. The coarray is different from the array itself. By coarray we refer to the processes. Okay, and we don't know ahead of time how many processes will be used. So we simply just put a star, which is allowed. Okay, for one-dimensional. Or if you like, if you want to specify some topology, explicit topology in parallel processing, then you can define a two-dimensional grid. So I want to use a 16 by 16 process grid, so that you can define a coarray in this way. Okay, and also coarrays. You can use the coarrays for single variable. Single variables as well. And here we define the two integers m and n, and they are coarrays, which means they are accessible among processes. As I pointed out previously, that with coarray, essentially you are using a SIMD, a programming model. So you write a single program, and then it depends on what the ID of your the process, the instance is. In this case, in Fortran, we call it image. Okay? And each participating instance of running program is called an image. So depending on the ID of the image, if the ID of the image returned by this call, by this function, this image, if the ID is 1, then I do this. If normally I would set 1 as the main or master image, then I'll input some data, and after I input the data, I'll do a broadcast, or broadcast the data to all the other images. How do I do a broadcast? A broadcast, I simply just push the value I just read, this, for instance, U here, and I push the value to use on all the other images. This is the typical broadcast. Next. Now, you can also use a coarray for derived data types. You define a structure. For instance, a particle. A particle contains the mass, coordinates, and the velocities. And you define an array of particles, which is 1 million elements, this particle. And this will be shared among all the processes. Okay. Or in the case of a dynamically allocated storage, and you can declare that this you can declare an array of particles, which is a structure particle, allocatable, and they are all shared. They're all shared among processes. Okay. Now, in this example, we define the coarray A, which is a single element, and coarray B. Okay, object A and B are coarrays, so they are shareable. They're shared among all the processes. And then I assign a value to A and a B. So now my value A contains the image ID, and the B is just 2 times the image ID. Okay. And then I want to access A and B later on. So if my image ID is 1, then I'm going to print out the message. So I'm going to print out the values. So this means when I write this program will be run in parallel, which means I write this program, a single program, and then when I run the program, I will run multiple instances. But I set a program in such a way that only the master program or the program with the image ID 1 will print the value of A and B, values of A and B. But now notice that I put a square bracket after A and B. Now, don't be confused with array notation. This is not array notation. This is array notation in C, but it's not in Fortran. This simply means I am printing. I'm printing the values of a single variable A and B on process I. Okay, this means I am printing the values of A and B on process I, not array A and B. Okay, and this is what's happening here. I'm printing the value with a square bracket I. I'm looping over all the images, so I will get the 1, 2, 2, 4, 3, 6, and so on and so forth. This is what we will see on image 1, because I write the code in such a way that if my ID is 1, then I will do this. Otherwise, then the other participating images will remain silent. Next, we'll just try to reiterate the concept here. This is a push. The push of Y to X. Both X and Y are single variables. And then here, we want to push B to A. Okay. And in the third case, we're fetching the value of Z and putting the local variable Z. Okay. And this is a typical selective execution. This is a typical way of writing a SIMD parallel program. So depending on the value, depending on the ID of the process, we will do different things. Here's a complete example. It's a broadcast. Now, I notice that we put a call to sync all around this if branch. This if branch, within this if branch, we're broadcasting the values I just read into Z and broadcasting the value of Z and by pushing it to the Z on other processes. Now, so what is the issue here? What is the performance issue here by doing the broadcasting this way? So by using a loop, we're looping over all the images from 1, 2, 3, and so on and so forth. We're doing the broadcasting in a linear way. And the complexity of this operation is O(n). But this is not efficient. And ideally, this is what we should do. We split this into branches, into 2 branches, and further, and we can end up with a log n. This is a more efficient way. But unfortunately, with the Coarray, with the kernel standard, it doesn't specify how we can do broadcast in a more efficient way, and we're looking for something, some improvement in the future. a summary of a single program multiple data model. So we declare coarray objects, A and B, and or this array, or in the case of a single variable. We just follow, we just put the square brackets after the regular variables to indicate that these variables or these objects are shared. And then we're using these important functions, this image, which returns the ID of the kernel image, and non-images, which returns the total number of images participated in the process, in execution. Okay, and in the control of workflow, typically you will do something like this. If the image, my ID is 1, then we do this, and otherwise we do this. For instance, if my image is 1, and I'll act as a manager. Otherwise, I'll work as a worker. And compiling Coarray Fortran. Now you have two options. You're using a GNU compiler. Then, in addition to the GNU compiler, you will need a library called the Coarray library. You need to download the Coarray library from Coarray project, and then when you compile the program, you need an MPI. You need an MPI to compile the Fortran program using Coarray with an option here, with an option f coarray equals lib. This is a GCC. This is a GCC an option, and also you need to use a standard equals F2008 standard. These are mandatory. Okay, and to run the Fortran program with the Coarray objects, you will run in MPI mode. You run MPI and a number of processes and compile the code. Or you can use an Intel compiler. And with the Intel compiler, you would need an option Coarray equals shared if your program is going to run on a shared multi-core system, for instance, on your laptop or desktop with the multi-cores. Or you want to compile with the Fortran, with the MPI. And the same thing, when you run compile the code, you will run in the MPI fashion, MPI, and then number of processes and the compile the code. Now, synchronizations. A synchronization, this is not just typical to Fortran. Synchronization is necessary for all parallel programs. Sometimes it's necessary that you won't do this, you will not execute this until everybody has come to this point. So it's a mechanism to synchronize among all the participating processes. And there are a number of ways of synchronize the participating processes. You can synchronize between images, among images, or you can synchronize among selected a set of images, just a subset of images. Again, this is a typical way of doing the parallel programming, depending on the ID of your image. They do different things, and then you can put this synchronization within the if branches. And I'll show you a last example. This is an example I gave to the students in last summer school. So what we want to accomplish is we want to assemble an image, a linear image. Was split. The image is being split into, for instance, here 4x4 tiles. And each process, we want to have each process to have a portion, to have a piece of the image, and do some work on it. And then in the end, we want to have the main process to collect all the images, all the pieces, and put them all together into the whole image. And how would you do that? The implementation, here are the key steps for implementation. So we use the pick, this is an array for the whole image, and I use another array, a pick underscore p for local portion. And we use a square bracket to indicate that this local portion, this local array will be shared among, will be accessible among by all the processes. And here's the snippet of the code. So if my ID is 1, I will loop over all the images. This is how I collect the images. I'll loop, this is how I collect the pieces. I'll loop over all the images. Now, remember, the images, here's the term for participating running programs, not this picture, okay? Loop over all the images or running processes, and I'm fetching a portion of image. I'm fetching a portion of the picture and put it into the whole. This is the whole picture. This is an array that it is holding the whole picture. Okay, very simple. Just one line of the code. I'm fetching the portion from process I or image I, which is could be just this small square. I'm fetching this little square and put it into corresponding location in my the whole picture array pick. And here it gives a little bit more code. So in your Fortran program, I will create a co-array object, pick underscore p. This is a local. This will hold the local portion of those pieces, and then I'll read this portion in some way. I already managed to organize the file in such a way that I can read individual pieces, and then I'll do some processing. And after that, after it's done, I am fetching this piece. For instance, here I'm fetching this piece from process I or image I and put it into the corresponding location in my whole array pick. And that's all. And there's no explicit message passing call. And everything is hidden under the hood. Okay. Okay, summary. Now this is just I put a few points. This is true for all the languages. Now, when you try to do projects and make a decision to what language to pick, you want to make a decision. You want to pick a language that can run on multi-core, and it can run on clusters and other supercomputers. And the language, the better it'll be expressive and productive, which means it's easy to write, it takes less time to write, and it's easy to read and maintain and reusable. And importantly, in addition, it should be efficient. So the code that you write and compile, it should be efficient. And also, the language should have a promised future of the availability and will last much longer. And as well, it better be supported by various tools. Okay, just to wrap up the talk, I'm just putting up references to some materials. So I'll just stop here, and we can take some questions from the audience.